Hello, everyone, and thank you for joining us. We will be presenting our senior project, Snowpack Measurement, a Data Collection and Model-Driven Approach. Our team consisted of 7 students, 3 mechanical engineers, as well as 4 electrical engineers. The purpose of this project is to measure snowpack using a drone in hard-to-reach areas in Colorado. These measurements are important because they pertain to water supply concerns, weather forecasting, agricultural operations, tourism and leisure, such as skiing and other outdoor activities, as well as climate research. We can provide value to our stakeholders by finding a better way to collect data, use that data for snowpack modeling and prediction, all at a lower cost. Our project consisted of a drone-based sensor development system, with the sensor package being deployed at different elevations between the ground and drone height. There are 3 major components of the system: the hexacopter drone with automated controls, the sensor package, which was Arduino-based with temperature, humidity, pressure, and altitude sensors, and last, our camera sensor with particle detection for measuring blowing snow.
Our first subsystem includes a hexacopter, the pulley mount system, and the tether cable system. We created an automated flight path for the drone using Ardu Pilot and a Pixhawk 4 control system. We designed and machined an aluminum plate to hold other attachments like the rotatable pulley and landing gear. The landing gear was 3D printed, and you'll see on the next slide that in order to use the alpha gel spring dampers for the tether, we had to design and machine a compressive plate attachment. This was also machined from aluminum. The pulley system was designed and part of it was machined from aluminum, except the cable guide, which we decided to 3D print. We were hoping to have an automated tether control system, but due to time and budget constraints, we had to improvise with what's shown.
We wanted to record atmospheric conditions near the drone. A simple solution was to use an Arduino Uno platform powered by a 9-volt battery. We were then able to use a data logger shield by Adafruit. We investigated a number of devices that recorded temperature or air pressure and other such phenomena. We chose a BME 280 barometer, which measures temperature, humidity, air pressure, and altitude. This device gave us multiple measurements on a single PCB, and so had the added benefit of keeping the sensor package weight down. The deployment system houses the Arduino data logging system and protects the electronics from ambient weather. This deployment system clamps to a pipe axle for the particle sensor system and Raspberry Pi. It also clamps to the tether, which is how it is moved up or down.
Early on in the project, we identified the need to make direct measurements of airborne snow and ice particles in the vertical cross-section below the drone. To accomplish this, we settled on building a vision-based particle sensor due to the low weight and cost of the design. The design uses a Raspberry Pi camera to record the passage of any particles through a small enclosure. The enclosure is strongly illuminated by LEDs and has a black backdrop to maintain consistent lighting. The video is recorded in a RAW format for post-processing. We also developed a weather vane style design to ensure that the enclosure opening is always facing into the wind. The enclosure rotates independently of the rest of the sensor package and the tether. After collecting raw data, we run computer vision post-processing. The raw image data is evaluated frame by frame, and each new frame particles are identified and counted. These are images of actual falling snow recorded by the sensor.
So after designing and testing our individual subsystems and confirming each of them was working successfully on their own, the next step was to combine them into integrated subsystems, test those, and then finally test the subsystems together as one final cohesive unit. This flowchart shows that the first integrated system, our control system, consists of the hexacopter drone attached to the tether by the pulley, and the second integrated system is our sensor package, which consists of the visual particle detection unit and the meteorological sensor and data logger system attached to the tether. Once these 2 subsystems were working, we combined them and tested the final integrated system. Our testing of the integrated control system went smoothly. We found that by introducing tension on the tether during the ascent and avoiding any sudden pull on the hexacopter at the moment of takeoff helped the drone to stabilize quickly. The Pixhawk 4 was able to hold the drone in position at a specified altitude of 15 meters, and a small payload was moved up and down the tether using the real control system. Here are a couple videos of the results. The left video shows the drone taking off. You can see there's initially a bit of slack on the cord there. In the second video, we move a small payload up and down the tether using the real system. You can see that the drone is able to hold position while the payload is moved up and down the tether. Our control system was working as hoped. Our second integrated system is the sensor package. We combined the meteorological and particle sensor system and mounted them together in clamping housings that allowed for the tether to move freely on one side while it was held in place on the other. The testing worked out as we hoped. The clamping held the tether in place without slipping, the windsock aligned with the wind to ensure that the sides of the particle detector unit wouldn't interfere with blowing snow, and the sensor package moved up and down without a problem. Okay, with both integrated systems working, it was time to combine them into our final integrated system. Unfortunately, this test wasn't as successful as the others. The combination of the added weight on the hexacopter for the pulley system and the weight of the sensor cart proved to be too much for our drone to handle. We did some modifications to the pulley system to lighten the drone, but it still wasn't enough. The video shows that the hexacopter can start to lift the drone, but there isn't enough thrust to accelerate the system upwards.
Although we had many successes with our subsystem tests, our complete integrated system did have some failure in that the drone system failed to adequately lift the sensor package. Our calculations showed that the drone should have been able to lift the package, but we suspect that variations in the performance of the drones versus their spec thrust ratings, that may be one cause, and also the package ended up weighing a little bit more than anticipated, about 30% more. Looking at those numbers, while we estimated that we should be able to lift at about 60% power, it looks like we were needing more like 90% power. And unfortunately, in the case of drones, you don't want to use 100% of your thrust to lift something, or even just sustain it in the air. You really need some extra thrust in order to be able to accelerate things. We believe that a larger drone may help solve this issue, but in the case of this study and our budget and our time constraints, this system just didn't quite work as we expected. Some key takeaways here. Our system works in theory. The subsystems were successful when tested separately. The full load test failed due to the weight limits and or the power of the drone. We suspect that maybe using lighter parts or a more powerful drone or more powerful motors may solve that. Another factor we experienced was wind can really make it difficult for these drones to operate. So one possible way to kind of rework this project is to, instead of use a drone, use maybe a pole or a cable to mount the same system. And a couple other improvements that could be made is the data collection and processing. It's all manual and every system is separate. It'd be nice to integrate all the systems together into one automated system. And then also, we just captured basically particle images with our particle detector, and it'd be nice to come up with a model that can translate that particle collection data into real snow data. This may require some scientific analysis, but it's outside the scope of what we were able to accomplish this semester. And then, of course, the reel system, we went with kind of a manual reel. Originally, we wanted to do an automated stepper motor controlled reel system. And we discovered that when manually running it, it's very hard to keep a consistent tension on the cable, and we tend to jerk the drone around when we're trying to manually move those. So it'd be nice to design an automated system to control that. So we wanted to thank our sponsors, Dr. Ethan Gutman, Dr. Scott Landau, Dr. David Yates, all at NCAR. They were our stakeholders for this project. And of course, our professors, Dr. Dan Jensen and Dr. Jeff Selman at CU, because they've supported us throughout this entire project. And then also Jack Corliss at the CU Denver at the Hub, who helped us with a lot of the machining work. And we thank you for your time and appreciate your attention.